The Alcubierre Drive or Alcubierre warp drive is a speculative idea based on a solution of Einstein's field equations in general relativity as proposed by theoretical physicist Miguel Alcubierre, by which a spacecraft could achieve apparent faster-than-light travel if a configurable energy density field lower than that of vacuum could be created, rather than exceeding the speed of light within a local reference frame. A spacecraft would traverse distances by contracting space in front of it and expanding space behind it, resulting in effective faster-than-light travel. Objects cannot accelerate to the speed of light within normal space-time. Instead, the Alcubierre drive shifts space around an object so that the object would arrive at its destination faster than light would in normal space. Even if it is physically meaningful, its mere existence does not necessarily mean that a drive can be constructed. The proposed mechanism of the Alcubierre drive implies a negative energy density and therefore requires exotic matter. So if exotic matter with the correct properties does not exist, then the drive could not be constructed. However, at the close of his original paper, Alcubierre argued that the Casimir vacuum between parallel plates could fulfill the negative energy requirement for the Alcubierre drive. Another possible issue is that, although the Alcubierre metric is consistent with Einstein's equations, general relativity does not incorporate quantum mechanics. Some physicists have presented arguments to suggest that a theory of quantum gravity would eliminate those solutions in general relativity that allow for backwards time travel and thus make the Alcubierre drive invalid. History. In 1994, Alcubierre proposed a method for changing the geometry of space by creating a wave that would cause the fabric of space ahead of a spacecraft to contract and the space behind it to expand. The ship would then ride this wave inside a region of flat space, known as a warp bubble, and would not move within this bubble but instead be carried along as the region itself moves due to the actions of the drive. It was thought to use too much negative energy until Harold Sonny White said that the amount of energy required could be reduced if the warp bubble were changed into a warp ring. Alcubierre metric. The Alcubierre metric defines the warp drive spacetime. It is a Lorentzian manifold that, if interpreted in the context of general relativity, allows a warp bubble to appear in previously flat spacetime and move away at effectively superluminal speed. The interior of the bubble is an inertial reference frame and inhabitants suffer no proper acceleration. This method of transport does not involve objects in motion at speeds faster than light with respect to the contents of the warp bubble, that is, a light beam within the warp bubble would still always move faster than the ship, because objects within the bubble are not moving faster than light. The mathematical formulation of the Alcubierre metric is consistent with the conventional claims of the laws of relativity, and conventional relativistic effects such as time dilation would not apply as they would with conventional motion at near-light speeds. The Alcubierre drive, however, remains a hypothetical concept with seemingly difficult problems, though the amount of energy required is no longer thought to be unobtainably large. Mathematics of the Alcubierre drive. Using the ADM formalism of general relativity, the spacetime is described by a foliation of space-like hypersurfaces of constant coordinate time t, with the metric taking the following general form, whereas the lapse function that gives the interval of proper time between nearby hypersurfaces is the shift vector that relates the spatial coordinate systems on different hypersurfaces, and is a positive definite metric on each of the hypersurfaces. The particular form that Alcubierre studied is defined by where and with arbitrary parameters, and Alcubierre's specific form of the metric can thus be written with this particular form of the metric. It can be shown that the energy density measured by observers whose fall velocity is normal to the hypersurfaces is given by where is the determinant of the metric tensor. Thus, because the energy density is negative, one needs exotic matter to travel faster than the speed of light. The existence of exotic matter is not theoretically ruled out. However, generating and sustaining enough exotic matter to perform feats such as faster-than-light travel is thought to be impractical. Lowe has argued that within the context of general relativity, it is impossible to construct a warp drive in the absence of exotic matter. Physics. For those familiar with the effects of special relativity, such as Lorentz contraction and time dilation, the Alcubierre metric has some apparently peculiar aspects. Its screw would be in free fall while accelerating without experiencing accelerational g-forces. Enormous tidal forces, however, would be present near the edges of the flat space volume because of the large space curvature there, but suitable specification of the metric would keep him very small within the volume occupied by the ship. The original warp drive metric and simple variants of it happen to have the ADM form, which is often used in discussing the initial value formulation of general relativity. This may explain the widespread misconception that this spacetime is a solution of the field equation of general relativity. Metrics in ADM form are adapted to a certain family of inertial observers, but these observers are not really physically distinguished from other such families. Alcubierre interpreted his warp bubble in terms of a contraction of space ahead of the bubble and an expansion behind. But this interpretation may be misleading because the contraction and expansion actually refers to the relative motion of nearby members of the family of ADM observers. In general relativity, one often first specifies a plausible distribution of matter and energy, and then finds the geometry of the space-time associated with it, but it is also possible to run the Einstein field equations in the other direction, first specifying a metric and then finding the energy-momentum tensor associated with it, and this is what Alcubierre did in building his metric. This practice means that the solution can violate various energy conditions and require exotic matter. The need for exotic matter raises questions about whether one can distribute the matter in an initial spacetime that lacks a warp bubble in such a way that the bubble is created at a later time. Although some physicists have proposed models of dynamical warp drive spacetimes in which a warp bubble is formed in a previously flat space. Moreover, according to Sergei Krasnikov, generating a bubble in a previously flat space for a one-way FTL trip requires forcing the exotic matter to move at local faster-than-light speeds, something that would require the existence of tachyons, although Krasnikov also notes that when the space-time is not flat from the outset, a similar result could be achieved without tachyons by placing in advance some devices along the travel path and programming them to come into operation at pre-assigned moments and to operate in a pre-assigned manner. Some suggested methods avoid the problem of tachyonic motion, but would probably generate a naked singularity at the front of the bubble. Alan Everett and Thomas Roman comment that Krasnikov's finding does not mean that Alcubierre bubbles, if it were possible to create them, could not be used as a means of superluminal travel. It only means that the actions required to change the metric and create the bubble must be taken beforehand by some observer whose forward light cone contains the entire trajectory of the bubble. For example, if one wanted to travel to Deneb and arrive less than 2,600 years in the future according to external clocks, it would be required that someone had already begun work on warping the space from Earth to Deneb at least 2,600 years ago, in which case, a spaceship appropriately located with respect to the bubble trajectory could then choose to enter the bubble, rather like a passenger catching a passing trolley car, and thus make the superluminal journey. Everett and Roman also write that, as Krasnikov points out, causality considerations do not prevent the crew of a spaceship from arranging, by their own actions, to complete a round trip from Earth to a distant star and back in an arbitrarily short time, as measured by clocks on Earth. by altering the metric along the path of their outbound trip. In conformal gravity, within the framework of conformal gravity, an extension of general relativity in which the angles of spacetime are locally preserved, the Alcubierre metric does not violate the weak energy condition for particular spacetime shapes, and hence faster-than-light travel would not require exotic matter. Difficulties. The metric of this form has significant difficulties because all known warp-drive spacetime theories violate various energy conditions. Nevertheless, Alcubierre-type warp might be realized by exploiting certain experimentally verified quantum phenomena, such as the Casimir effect, that lead to stress-energy tensors that also violate the energy conditions, such as negative mass energy. When described in the context of the quantum field theories, mass energy requirement, if certain quantum inequalities conjectured by Ford and Roman hold, then the energy requirements for some warp drives may be unfeasibly large as well as negative. For example, the energy equivalent of minus 1064 kilograms might be required to transport a small spaceship across the Milky Way, an amount orders of magnitude greater than the estimated mass of the observable universe. Counter-arguments to these apparent problems have also been offered. Chris van den Broek of the Catholic University of Leuven in Belgium, in 1999, tried to address the potential issues by contracting the 3 + 1 dimensional surface area of the bubble being transported by the drive, while at the same time expanding the 3-dimensional volume contained inside. Van den Broek was able to reduce the total energy needed to transport small atoms to less than 3 solar masses. Later, by slightly modifying the Van den Broek metric, Sergei Krasnikov reduced the necessary total amount of negative mass to a few milligrams. In 2012, physicist Harold White and collaborators announced that modifying the geometry of exotic matter could reduce the mass-energy requirements for a macroscopic spaceship from the equivalent of the planet Jupiter to that of the Voyager 1 spacecraft or less, and stated their intent to perform small-scale experiments in constructing warp fields. White proposed changing the shape of the warp bubble from a sphere to a torus. Furthermore, if the intensity of the space warp can be oscillated over time, the energy required is reduced even more. According to White, a modified Michelson-Morley interferometer could test the idea. One of the legs of the interferometer would appear to be a slightly different length when the test devices were energized. Placement of matter. Krasnikov proposed that if tachyonic matter cannot be found or used, then a solution might be to arrange for masses along the path of the vessel to be set in motion in such a way that the required field was produced. But in this case, the Alcubierre Drive vessel can only travel routes that, like a railroad, have first been equipped with the necessary infrastructure. The pilot inside the bubble is causally disconnected with its walls and cannot carry out any action outside the bubble. The bubble cannot be used for the first trip to a distant star because the pilot cannot place infrastructure ahead of the bubble while in transit. For example, traveling to Vega requires arranging everything so that the bubble moving toward Vega with a superluminal velocity would appear. Such arrangements will always take more than 25 years. Kuhl has argued that schemes, such as the one proposed by Alcubierre, are infeasible because matter placed en route of the intended path of a craft must be placed at superluminal speed, that constructing an Alcubierre drive requires an Alcubierre drive even if the metric that allows it is physically meaningful. Kuhl further argues that an analogous objection will apply to any proposed method of constructing an Alcubierre drive. Survivability inside the bubble. A paper by Jose Notario argues that crew members could not control, steer or stop the ship because the ship could not send signals to the front of the bubble. A more recent paper by Carlos Barcelo, Stefano Finazzi, and Stefano Liberati uses quantum theory to argue that the Alcubierre drive at faster than light velocities is impossible, mostly because extremely high temperatures caused by Hawking radiation would destroy anything inside the bubble at superluminal velocities and destabilize the bubble itself. The paper also argues that these problems are absent if the bubble velocity is subluminal, although the drive still requires exotic matter. Damaging effect on destination. Brendan McMonigal, Geraint F. Lewis, and Philip O'Byrne have argued that when an Alcubierre-driven ship decelerates from superluminal speed, the particles that its bubble has gathered in transit would be released in energetic outbursts akin to a sonic boom shockwave. In the case of forward-facing particles, energetic enough to destroy anything at the destination directly in front of the ship wall thickness. The amount of negative energy required for such a propulsion is not yet known. Fenning and Alan Everett of Tufts hold that a warp bubble traveling at 10 times light speed must have a wall thickness of no more than 10⁻32 meters, close to the limiting Planck length, 1.6 times 10⁻35 meters. In Miguel Alcubierre's original calculations, a bubble macroscopically large enough to enclose a ship of 200 meters would require a total amount of exotic matter greater than the mass of the observable universe, and straining the exotic matter to an extremely thin band of 10⁻32 meters is considered impractical. Similar constraints apply to Krasnikov's superluminal subway. Chris van den Broek recently constructed a modification of Alcubierre's model that requires much less exotic matter but places the ship in a curved space-time bottle, whose neck is about 10⁻32 meters. Causality violation and semi-classical instability calculations by physicist Alan Everett show that warp bubbles could be used to create closed, time-like curves in general relativity, meaning that the theory predicts that they could be used for backwards time travel. While it is possible the fundamental laws of physics might allow closed time-like curves, the chronology protection conjecture hypothesizes that in all cases where the classical theory of general relativity allows them, quantum effects would intervene to eliminate the possibility, making these spacetimes impossible to realize. Some results in semi-classical gravity appear to support the conjecture, including a calculation dealing specifically with quantum effects in warp drive spacetimes that suggested that warp bubbles would be semi-classically unstable. But ultimately the conjecture can only be decided by a full theory of quantum gravity. Miguel Alcubierre briefly discusses some of these issues in a series of lecture slides posted online, where he writes, "Beware. In relativity, any method to travel faster than light can in principle be used to travel back in time." In the next slide he brings up the chronology protection conjecture, and writes, "The conjecture has not been proven, but there are good arguments in its favor based on quantum field theory. The conjecture does not prohibit faster than light travel. It just states that if a method to travel faster than light exists, and one tries to use it to build a time machine, something will go wrong. The energy accumulated will explode, or it will create a black hole." Experiments. In 2012, a NASA laboratory announced that they had constructed an interferometer that they claim will detect the spatial distortions produced by the expanding and contracting space-time of the Alcubierre metric. The work has been described in Warp Field Mechanics 101, a NASA paper by Harold Sonny White. Alcubierre has expressed skepticism about the experiment, saying, "From my understanding there is no way it can be done. Probably not for centuries if at all." In 2013, the Jet Propulsion Laboratory published results of a 19.6-SECOND warp field from early Alcubierre drive tests under vacuum conditions. Results have been reported as inconclusive. Relation to Star Trek warp drive. The Star Trek television series used the term warp drive to describe their method of faster-than-light travel. Neither the Alcubierre theory, nor anything similar, existed when the series was conceived. But Alcubierre stated in an email to William Shatner that his theory was directly inspired by the term used in the show, and references it in his 1994 paper.